We've spent some time so far discussing how the height of binary search trees can change over time. So now I'm going to introduce formally what height means, what depth means, and what average depth means. And we'll see how that relates to operations. So height we've already been referring to informally, and to formalize it, I'll start by telling you about depth. The depth of a node is how far it is from the root. So for example, here is the root, here is E, here is G. It is 2 links away from the root. So we say its depth is 2. We can think of our tree as a sequence of depths. So we have the root at depth 0, we have 2 nodes here of depth 1, 4 of depth 2, 6 of depth 3, and 1 of depth 4. Now the height of a tree is just the depth of the deepest leaf. So in this case, the height of the tree overall is 4. And then the average depth of a tree, which we'll see as a useful concept, is the average depth of a tree's nodes. So for example, we have 1 node at depth 0. We have 2 nodes at depth 1. We have 4 nodes at depth 2. We have 6 nodes at depth 3, 1 node at depth 4. And so if we add all of that up and we divide by the total number of nodes, we get 2.35. So this tree is very close to the optimal depth. If we move the S up 1 level, we would be at the theoretical minimum. So this is just a little worse than that theoretical minimum. So what do these have to do with our operations? Well, the height of a tree determines the worst case runtime for finding a node. So for example, if we're doing a contains operation on a set. So if I wanted to say, does a set represented by this binary search tree contain S? Well, we'd take 5 comparisons. We'd go 1, 2, 3, 4, 5. And that would be the height plus 1. And then the average depth gives us the average runtime to find something. So if I do a random contains operation, on average it will take 3.35 comparisons, which is the average depth plus 1. So let's try and understand how often, under what circumstances we end up with spindly versus bushy trees. So let's say we want to build a binary search tree out of the numbers 1, 2, 3, 4, 5, 6, 7, and I'd like you to give me a sequence of add operations that results in a spindly tree versus a bushy tree. So the spindly should be relatively easy. Oops, we're missing a line. That's mysterious. Let's fix it. But yeah, so I'll let you start thinking about this. You can pause the video. I'll give you my answer once you're ready. Okay. So the spindly tree, it can be created by adding items in order, whereas the bushy tree, this is actually a little trickier, but the basic idea is if I add the median first, that's 4, and then I add the 2, and then I add 1, then I add 3, that will get me the left side. If I then add 6, then 5, then 7, I'm in good shape. What matters here is that I'm adding 6 before 5 or 7, and that'll ensure we get this nice shape over here. So the difference between these two trees is a height of 6 versus a height of 2, or an average depth of 3 versus an average depth of 1.43. Remembering that this is the worst case runtime, and this is the average runtime for a random operation. So we now see that with the same exact items, we can get 2 totally different tree structures. And the only thing that matters is the order in which you add things that determines the shape. So what we know now, and have seen in great detail, is that in the best case we have log n height, in the worst case it's n height. And so now the question arises, namely, what about trees that you'd build during real-world applications? If I'm using a set to keep track of, I don't know, members of my club or whatever, what's going to happen? Am I going to get something that looks spindly, something that looks bushy? And so one way to approximate this process is to consider totally randomized BSTs. So this is a simulation created by Kevin Wayne at Princeton, where I used to work. And what it does here is it randomly adds items to an initially empty tree. So to pause for a moment, here, this max is the height plus 1, and then average is the average depth plus 1. You can think of this as the runtime for the worst case contains and the average case contains. So as it's running, we can see that the tree, even though we're adding items in a totally random order, it is fairly bushy. I mean, the opt here, this represents the theoretical optimum average depth, and while we're not as good, we're close. What you'll see is we don't have some giant 200 long chain. So it's not as bushy as if we did things perfectly, but you can show, and we will later in this class, that on average you actually do end up with a theta log n average depth and height. So it is bushy. That's good news. Random trees are bushy, not spindly. Now there has been mathematical analysis done. You can show, and we will in class, that if we insert keys into a binary search tree, the expected average depth is tilde 2 natural log n. And this tilde here represents something kind of like theta, where you just don't drop the leading multiplicative constants. So we're not going to do this proof in total detail, but we will see why much later in the class. And so what that tells us is that the average runtime for the contains operation will be theta log n on a tree built with random inserts. Now what about the height? Well, this is actually a much harder proof. So this proof is only actually from 2003, which is kind of amazing because the binary search tree is such a basic mathematical object. And yet this proof came decades after binary search trees were invented. So if we insert in distinct things into a binary search tree, the expected height is actually 4.311 natural log n. And we're not going to talk about this proof at all. It's actually a 27-page proof. And what this tells us, though, the bottom line, the important part, is that the worst case runtime for contains operation will be theta log n if you insert randomly. So this seems like great news, right? It sounds like we're not really in bad shape. Yeah, you can get spindly trees, but random trees are fine. That is, whereas the worst case for a binary search tree is theta n, if we randomly insert things into a tree, we end up at our best case theta log n. Now, one potential issue is that, of course, in the real world, you expect our trees to have insertion and deletion if we're using for real-world tasks. So if you're curious about that, you can see the extra slides where we discuss a simulation that also includes deletion. But the end result of all that is that we can show that random trees, even if we're randomly inserting and deleting, are still theta log n height. So it seems like this is great news. We're good to go. But there's one really big danger. So the good news is if we randomly insert items, our tree will be balanced. It'll be theta log n with very high probability, and that actually also applies if we insert and delete randomly. The bad news is, however, we can't always insert our items in a random order. If we could, we would have guaranteed, with very high probability, balance, but this isn't possible in real-world scenarios. So consider why this might be the case. Okay, so it's actually kind of a silly reason, kind of obvious in retrospect, which is that data comes in over time. We don't have it all in advance. So imagine we have a system where we're storing events that occur on a security camera. So I add, for example, that I saw someone at 10:31 in the morning on January 1st, at 6:51 p.m. on January 1st, and so forth. These are in order, and so if naively we insert these into a set, it'll end up very spindly. Now this is a bit of a contrived example, but it turns out this is something you really have to worry about. If you're just taking data, it is possible that it's going to come at you in such a way that it causes your tree to become horrible and spindly. And so in this lecture, we're going to do something totally different to make this actually impossible, no matter what order events come into our tree, so that it is always nice, beautiful, bushy, and balanced.